See if we get this share screen working. Can you see that, Steve?
Yes, looks
All
good.
right, very good. All right. Well, thanks everyone. Appreciate being here, and I wanted to just talk a little bit about subbases and subgrades today. What we're going to talk about a little bit is performance of subbases and subgrades and how we can improve those for good quality concrete pavements. And before we get into that, I wanted to just talk a little bit about the CP Tech Center. And the CP Tech Center is housed at Iowa State University, and it's a unique group of professionals there. You can see the professionals there. Peter Taylor, Dr. Taylor is the director of CP Tech Center with assistants from Gordon Smith, Steve Treesh, and John Adam. And the neat thing about the center is they represent the three groups there shown in the graphic. They all come from each of the three groups of agencies, whether it be state DOTs, county or cities, the agency, the industry groups, paving association, and academia. So with those three groups interacting, the CP Tech Center is kind of the nexus of that, and they do a good job of sharing information and helping others understand concrete pavements and what can be done to improve performance of concrete pavements, and sharing technology, doing technical transfer, problem solving, and just overall building better concrete pavements. So I encourage you to visit the website. There's a lot of material there, cptechcenter.org. You can get in there and look at webinars that have been published recently. We've done a lot of webinars in the last year, and different research documents. There's a lot of good information on the website. Steve already kind of introduced me, so we'll skip past. There's my contact information. I'll have that at the end as well. But I have worked a little bit with cement stabilized subgrade soils and subgrade performance and subgrade testing and research, but I am not a geotechnical engineer. My specialty is in concrete pavements, so I come from that point of view. My approach is the performance of concrete pavements, but if I can't answer any specific detailed geotechnical questions, I sure know a lot of people that we can get you the answer for. So what I'd like to talk about today is just some general information on concrete pavement support and what we're looking for regarding what kinds of support structure or foundation systems are we after when we're developing the support structure for concrete pavements. We'll talk about soils and subgrades, subbases, geotextiles, some chemical stabilization techniques, which was pretty new and up and coming. We developed a guide recently on cement stabilized soils and current research as well. So just covering the bases here, we don't need a strong subgrade for concrete pavement, but we want a uniform subgrade. So what we have to do is prepare the soils, understand what we're dealing with in that corridor, to understand what kind of soil it has, what kind of characteristics, and how is that soil going to behave over time. So for concrete pavements, we're really after uniformity and non-erodible support. If you look at the graphic there, if you take a 100 psi load on an 8-inch slab, only 3 to 7% of that load, or 3 to 7 psi, is going to transfer to the subgrade. While that's not much, it does require some uniform support. And as I talk about later, you'll see what kinds of issues you can have if you have variable subgrade support conditions and voids developing under pavements. I think we all know what happens when we have voids under pavements. We can lead to cracking and failure mechanisms. So conversely to a flexible pavement system where we need a rock subbase, and we need strength, a strength layer to support vehicle loads as part of the structural pavement system. The subbase, or the support system for concrete, is really all it's after is uniformity. You can see in the graphic there that we're really after a stable working platform. When we talk about subbases and different subgrade treatments, whatever we can do to improve the working platform will help with uniformity, but it will also expedite construction operations. So naturally, when you're working with a slab on grade, just a typical concrete slab on subgrade, and you have a rain day, what do you have to do? You have to disc and dry out the soils, and you're shut down for at least a day while that subgrade is drying out. If you have a construction platform, say with aggregate subbase or a chemical treated base of some kind, you will have a better working platform. So it provides working platform, can speed up construction, and also provide a expedited construction operations technique. As I said, subgrade uniformity is important. If you go back to ACPA and some of their publications back in 2008, they did a sub-base document, some guidance there. And what they're saying really is uniformity of the subgrade and subbase layers is more important than its strength. So it's just emphasizes what I've just said. We're after uniformity. Uniformity of the subgrade and subbase layers avoid stress concentrations, reduces pavement deflections from vehicle loadings. So it does little to improve, providing just a subbase layer does over a non-uniform subgrade does little to improve uniformity. And so I'll talk about this study that Dr. White was involved with, just released January of this year. We'll show some information from that research study. So just throwing rock on the subgrade is not going to provide uniformity if you don't have a prepared uniform subgrade to begin with. So I think we all can understand that. So getting into the soils a little bit, if you think about the soil classification systems and what types of soils we're dealing with, primarily we're looking at sand, silts, and clays, right? So you can see the different sizes of the particles we're dealing with sand being 10 times larger than a silt particle, and silt being 10 times larger than clay, and the clay is actually 1,000 times. You can see these magnification there of how much you have to zoom in to see those particles. And so we're dealing with different structures and different sizes of particles. And if you think about a sand and gravel layer, you think about a system that is relatively permeable, so you can run water through it. If you're at a beach, you dump a bucket of water on the sand and it runs right through, right? So there's a lot of void space between those sand particles that allow the water to run through. You get into silts and clays, however, that's where we're dealing with low permeability. So two primarily different functions there. Sands and gravels are great for drainage properties, and sometimes if we have open graded gradations, open graded aggregate shapes and gradations, we can have really good drainage, but sometimes you may have some concerns from consolidation after repetitive loading, and you can get some variation in the thickness of that rock subbase. So that's something you need to pay attention to. If you go to silts and clays, those can really pack in tight. You can get really dense support systems with silts and clays, but you don't get quite the permeability, as we all understand. I found this map of Michigan soils, and what you see there is a variety of different soils. So similar to Iowa soils and other Midwest states, you have a variety of silts, clays, sands, and gravels all over that's basically deposited after the glacial retreat. So you have different soils, and your often challenged with providing the best subgrade support system, but you're dealing with different soils. So the number one thing I like to do is develop a great relationship as a design engineer, a pavement designer, develop a great relationship with a geotechnical engineer that really knows the soils and can comment on the classification of soils and how they're going to perform, with freeze thaw and volume change with when they gets in the presence of moisture. You can have swelling clays that swell, shrink and swell, so that volume change can be a concern, obviously, with your subgrade support system. So get a geotechnical engineer involved on each of your projects, understand what soils you're dealing with on each project, because they can really impact the performance of your pavement. So if you think about the soil classification chart, if you want to split it into two groups, and you can go back to that slide with silts and clays on one side and sands and gravels on the other, there's two different divisions there. And when you look at sands and gravels, you're looking at cohesionless particles that, sands and gravels don't stick together. They have point-on-point contact and provide great permeability, but they don't stick together. On the other hand, you have cohesive soils, and these are our clays. We deal with clays all over the Midwest, and clays are soils that can stick together. They perform differently. As I said, when they get wet, they can change state from a solid state to a liquid state with the addition of water. So cohesive soils, you can shape and put bond together into different volumes. So they obviously are going to perform different. And you think about the plastic range of soils, and you're thinking of the plasticity index. If you go back to the Atterberg studies that some of you have done back in college when you played with soils in the soils lab and you rolled up the soils into different little shapes, excuse me. The biggest takeaway from the Atterberg limit scale as you look at the different states of soils is that plasticity index, this PI. So the PI has a great importance when you're thinking about subgrade support systems. You want to have subgrade support material that has a low PI. If you have a soil that has a large PI, that plastic state, the difference between the plastic limit and the liquid limit is large. That gives you more risk for volume changes, expansive soils, shrinkage while drying, those types of things that can be pronounced when you're looking at long-term pavement performance. So we'll talk about that PI value here as we go.
Jared, I have a question for you.
Sure, go ahead, Steve.
Can you define non-uniformity in subgrade soils? What do you mean by non-uniformity in terms of plus minus percentage or plus minus a modulus value? In other words, if you've got, let's say, a 3,500 PSI soil, that's the modulus, what would be considered non-uniform soils if in terms of that, or in terms of, CBR or what?
That's an excellent question. And I guess in my opinion, if you're looking at modulus, the 3,500 if I could go plus or minus 250 PSI, if I can go 3,250 to 3,750, it's a pretty uniform soil. I also want to look at the visual aspects of that soil. If you're seeing different coloring with the subgrades as you're out there preparing subgrade, and you have variability in color from one station to the next, over a couple hundred feet or less, that variability in color is going to tell you there's a different soil property going on there, and that's a non-uniform soil. So not only with modulus, but also the visual appearance of uniformity. That's an excellent question, and I think a geotechnical engineer could probably explain that a little more. But in my opinion, I think, if you're looking at modulus values, that, plus or minus 250 would be a good range based on what I've experienced. But
okay, good. Thank you.
CBR values, you know, that 3,500 PSI is okay. In Iowa, we deal with pretty poor soils, and you probably have them too in Michigan, where they're great for farming, but not the best for road building. So we typically always have to do something with the subgrade to get it prepared and ready for a support to perform as a foundation layer. So if you think about different problems with the working platform or subgrades, you know, everyone's probably seen situations or been involved with a project where it's just, you just can't get compaction, or you're losing equipment in the mud. And that has to do with that plasticity index. If you have that high PI, that range, you're going to have variation with even just a little volume change. A little moisture addition to that soil can create some havoc on your subgrade performance. So just a list there: expansive clays, weak soils, poor support. You know, a lot of times back in the old days, we could disc subgrades and let them dry out and be on our way, and just our only cost is time. Nowadays, time has value, so we got to keep moving. And so we'll talk about different treatments of how to improve these subgrades to get better performance. There's a lot more soils information that you can go into, but we'll segue into subbases now. Excuse me. So we think about subbases, and I'm talking about the aggregate rock layer that's typically located on top of your prepared subgrade. And most of these subbase layers have some kind of drainable quality to them, depending on the number of fines. And when I talk about fines, I'm talking about percent passing the 200 sieve. We look at gradation values or gradation ranges, and we look at the number of fines. If you have a high percentage of fines over 10%, for example, passing the 200, that's going to give you more of a compactable subbase. So, but overall, the subbases are going to give you good permeability. We tend to use those subbases to, I like to call them an insurance blanket, if you will, that helps provide a working platform, provides uniformity, as I said earlier, only if subgrade is uniform. So if you throw a rock layer on top of a non-uniform or subgrade that's not passing the proof roll test, it's going to be reflected in that subbase layer. Drainage is very important when it comes to concrete pavements. So I think a lot of us have seen the effects of moisture in our pavements, whether it's freeze thaw damage or joint deterioration from substandard materials or the way it was constructed. We got to do everything we can to get the drainage away from the pavement. If you saturate a pavement over several years, you will see distresses crop up, and there's so much you can do to try to keep that system dry, and that's includes developing a subbase system with a subdrain layer. So that little graphic there on the screen, got to have a subdrain layer, unless you're in a very high permeable sand and gravel type soil layer where you have good permeability. But most often in the Midwest with our clay soils, we got to have a place to take the water. Can provide a cutoff layer from subsurface movements, reduces shrink and swell potential based on volume changes of that subgrade layer. You got to have that subdrain outlet. Let's look at granular subbase types. If you think about, as I mentioned, that a dense system in Iowa, it's called a Class A. I apologize for the Iowa terminology here, but Class A rocks in Iowa, a gradation would have a higher percentage of fines passing the 200. And so that's going to provide you with good stability, good density, but low permeability. So good stability, low permeability. If you go to a highly permeable and open graded aggregate system, you're going to have great drainage, very permeable, but sometimes you're going to get some low stability If you have many years of heavy truck traffic or that sort of thing where you have potential to consolidate that rock over time. And what Iowa does is they pick, they do have granular subbases and open graded mixes. I think the most common subbase in Iowa that's used is a modified subbase or a special backfill, which includes recycled concrete pavements and that sort of thing. So it provides kind of a system that meets both stability and drainage criteria. So subbases for strength for concrete pavements, we should all know as we're designing concrete pavements that we're not going to get a lot of reduction in pavement thickness by adding rock to the foundation support system. So this graphic from ACPA says, you may, with a residential street, you may be able to reduce your pavement thickness by, say, a ½ inch or an inch. If you increase your K value from 100 up to 2 to 300 PSI per inch, that's a pretty, you're putting a lot of effort to improving that foundation layer, not getting a lot of benefits. So we're not using aggregate under concrete pavements for strengths or for reduction in pavement value, reduction in pavement thickness. It's more about a drainage layer, working platform, that type of thing. Some other charts that prove that point is this comes from an Iowa research study where we looked at working with MEP, DG, or the pavement ME model. It's a software design model, pavement thickness design that is able to look at different failure mechanisms in concrete. And with IRI smoothness, if you have a pavement without any rock layer, you tend to have a higher over time, over a design life of say 20 or 30 years, you're going to have higher IRI inches per mile. If you add rock to the system, it's going to drop that IRI and perform. And these are end of life failure modes. So if you look at a roadway with 1,000 vehicles per day, this is pretty low traffic, by the way. What you see here is a leveling of the curve. So by the time you get to 5 inches of subbase, you're not getting a lot of benefit for being able to provide. You're still going to get a smooth roadway, whether you have 5 inches of subbase or 12 inches of subbase. So that road isn't going to fail in year 20 based on faulting or inches per mile rideability. So the same thing is true when you look at cracking. You see that those curves dropping off, they level off. So about that 5 to 6 inch value of subbase thickness, after that, you're not getting a lot of benefit for a reduction in design life or a reduction of cracking after 5, 6 inches of subbase. So there's not, again, we're not putting subbase in there for strength. We're not, it's not going to help us in long-term faulting or long-term cracking failure mechanisms. It is a good thing to do, but you don't need to put in 10, 12, 15 inches of rock to improve pavements that would normally fail by cracking or faulting, is what those two slides show. So what are our options when we get to a project site and we're looking at, okay, we need to improve the foundation in some way. Again, this is from top to bottom, we're looking at level of cost, level of effort that needs to be done to improve the subgrade or improve the soils. Scarifying and drying at a minimum. We typically have to get rid of any organic layers, layers that are the dark black soil that's great for growing vegetation. We got to get those out, stockpile them. We need to get to the clay, scarify and dry and compact. That's number one. If we see some of those variations in color that I spoke about earlier, what you can do is do some blending. So I know we're doing disking already, but we can take it one step further and do some blending of soils to try to get that uniform color. If you're seeing different non-uniform color in your subgrade soils. As you go on, and some of these mechanisms aren't enough, so you're looking at a proof roll test, for example. There's other things we need to do to improve the subgrade layer and spend more effort beyond just scarifying, drying, beyond blending soils. So we're looking at geogrids and a geogrid and subbase system. We're also looking at chemical stabilization. Those two are probably more equal. They're when it comes to level of effort and cost, they're probably about the same, and they provide good benefits to the subgrade performance. And then finally, if all else fails, you can always remove and replace. So coring out subgrade soils, that's going to be your most costly option. It's going to take the most time and effort to remove and core out subgrades. So those are the things we want to try to avoid when it comes to improving subgrade performance. Geotextiles, I'll just go through real quick. There's woven geotextiles. They're higher strength, provide some strength and support. They have some drainage properties. They geotextiles, whether they're woven or non-woven, provide separation between the subgrade soil and for example, a subbase rock on top of that. So it's a good system. If you're looking at separation, you can use these materials to provide a separation layer and provide drainage through those geotextile layers. The non-woven is not quite as strong as the woven materials, but they do provide good separation as well and provide good permeability. Geogrids are good as well. And again, you're going to get into a little more effort and probably a little more cost when you're going to the geogrid system. Nowadays, there's the triangular or triax system of geogrids that are do a very good job of providing stability. Biaxial geogrids, the square pattern geogrids, also do a good job. But you have to have the system operating together. You have to have the right aggregate subbase sizes that complement the aperture size of the geogrids. So it's important to talk with your geogrid supplier and make sure they understand what you're after for improvement in subbase or subgrade or foundation layer improvements. And they can typically help you with some different options of geogrids and rock sizes together. That's just a DOT specification example there. So with the geogrids, they really provide a lateral stability. It really spreads the load laterally. So if you think about subgrade layers that are wet and wouldn't pass a proof roll test, what that geogrid does is with the rock, they work together and provide a lateral spread of that loading, so we can spread that over a larger distance. So another option is chemical stabilization, and we're looking at adding chemicals to the subgrade and mixing them, typically adding water to change the properties of the support structure and firm that subgrade up to get it into a uniform condition. Fly ash is one technique, and I think I've seen over the years different geotechnical reports will recommend a fly ash percentage of 15 to 18%, which I think over the years that fly ash amount has gone up. Typically, I think we could get good performance out of 10 to 15%, depending on what exactly is going on with the subgrade soils. But that is one technique. Quick lime is also another product that can be used for chemical soil stabilization, and you're looking at a lot less product with quick lime, whether it's dolomite or a high quality lime. And then finally, cement modified soils, another technique for chemical stabilized improvements. So you can see there fly ash and lime. There's been a few studies shown that fly ash is great getting you that improved workability and improved construction platform, just like lime and cement. There was one study in central Iowa where we've seen a potential weakening of subgrade layers tested after the fact during a spring thaw. So there's been some research that shows there's some potential for weakening or change over time based on moisture levels. So that I think that needs more study. Quicklime is also a good product, but it reacts slower than fly ash, and it can provide some expansion properties. Both create a good wet working platform. The Cement Stabilized Subgrade Soils Guide came out last year, and back in May, and this was published from the CP Tech Center. A group of very talented geotechnical engineers, pavement designers, folks that work in the cement industry for stabilization, came together, served on the technical advisory committee, and put this guide together. This is available on the CP Tech Center website as well. Just came out last year if you're looking at another type of technique. And I'll spend a little time on cement modified soils. And basically in a nutshell, what we're doing is we're integrating cement in our soils, adding water and mixing it up, and then changing those properties and providing a working platform. There's a slight difference between CMS and CSS, where CSS provides more strength, more bearing strength than a CMS, and it also you get there by adding a little bit more cement, but they're very similar types of subgrade stabilization techniques. What we use cement stabilized soil for is to improve that the performance, eliminating removal and replacement of inferior soil. So basically we can treat all of our soils in place. We don't need to harvest to core out soil and improve it and bring it back, or bring in fresh material. We can work with what's there. And a lot of times just by using 2 to 4%, I would say for CMS, or up to 5-6% for CSS, you can really improve the performance of that subgrade. Forms an all-weather work platform that doesn't change over time. Years later, you can go back and you still have those performance improvements. You can go back and test those. If you really want to study the science between cement stabilized soils, I encourage you to go to the guide. Excuse me. But I'm not going to get into this, but I did want to comment on the different, the timing that each of these 4 steps take when you're doing cement modified soils. Cation exchange, particle restructuring, hydration, that's all done up front during that initial mixing to a few hours, up to 28 days for the hydration process. And then the pozzolanic reaction takes more time. So there's different things going on with that modification mechanisms with cement stabilized soils. If you look at different options, this table's a pretty good summary of how to treat different soils. So if you look at your AASHTO and USCS soil classifications, there are some asphalt products that will treat a good share of different soils, problematic soils. If you look at cement and fly ash treated soils, that technique will treat a good majority, if basically maybe 80% of our soils that are on the classification system. So I think as we see potential for fly ash supply being harder to find in the future, or use that fly ash in our mixes, I'd rather maybe use a fly ash product in our concrete mixes for durability. I think we'll see more of cement treated subgrades going on out in there. So So clay soils, the A6, A7, these cement treated subgrades will treat all these different properties. So expansive soils, low permeable soils, soils that just don't dry out. Cement treatment will go a long ways to treating these types of soils. Similarly with silty and sandy soils, those A4s, the silts that just are difficult to compact and have very poor performance as a subgrade layer. These A4s, A3s, and A5, A6, A7, these are all treatable soils with cement stabilization. And there's really two different paths if you're doing CSS. There is a design, if you know ahead of time that you have problematic soils, you can follow the flow chart in the book. If you follow the right line of the flow chart, if you know ahead of time that you're going to have an issue. So that includes collecting soils for lab testing and different gradation analysis and different tests, and coming up with a mixed design for CSS. If you're in the field and this is a surprise, then you have to rely on, again, our friend, the geotechnical engineer, for different cement percentage ranges that you can try to incorporate during construction. So you bypass those laboratory tests and just go out there and start mixing the cement in the soil. I'm going to skip through these real quick because I know we're going to get long on time, but these are just the steps of the CSS mixture design. You really need to know a lot about your in situ moisture content, and you have to hire that geotechnical engineer to classify your soils. We need to look at different cement types. Typically, type 1, type 2 cements are common for cement treated bases or subgrades, excuse me. But if you have different different types of soils where you have incompatibilities through say high sulfate, if you will, in different parts of the country. For example, the blue in this figure here shows soils high in sulfate. So through the Dakotas, Nebraska, down into Texas, you have high sulfate soils. So if you have high sulfate in your soil in Michigan, doesn't look like it's on the category for sulfate as far as this map goes. But then in those situations, you have to pick different cements, like a type 5 or type 2 cement that will react well with the hydration process.
Jared, we've got a couple of questions. Can we
Absolutely.
answer
I can
some?
take a drink.
Yep. Okay. First one is this. Has anyone tried to use a combination of recycled concrete fines with cement or fly ash?
I'm not aware of that, but that's not a, I wouldn't rule it out. I'd probably want to do a test run and see how it works. Okay. You do have more fines in your recycled pavements, whether it's recycled asphalt or recycled concrete. So there are some granular materials. I think that may have some probability of good performance. I think I'd like to do some testing though on that. That's okay. A good question.
Yeah, that's coming from the fact that we in Michigan do a lot of recycling of our existing concrete pavements, typically as a base material under new pavements. But what is screened off and unable to be used typically because we want a permeable, drainable base material is the fines, the chips and dust.
Yep.
So that's where that question is coming from.
Okay, now that you say that, I understand it a little better. Absolutely. I think you could do a treatment to the subgrade, obviously with some cement or fly ash, and do some subgrade improvement, and then follow up with a recycled base.
Okay.
I think that's been done several times.
Gotcha.
But not all at one.
Yep.
I do it in two separate operations.
Okay. Next one. Are these similar to the cement treated permeable base that we are starting to use? That question came in about 5 or 6 minutes ago, so I'm not sure which slide that is in reference to. So, but I will say in Michigan, again, we take our existing concrete, crush and reuse as a base material. And then we've, on some projects, instead of using it as an unbound recycled concrete base, we're using it with primarily cement as a binder, more to tie up some of the, again, that chips and the dust that we're trying to screen off, but some of that stays in and creates some leachate, some calcium carbonate, which can potentially plug up geosynthetics, as well, separator fabrics, as well as potentially the sub-drainage systems, under drains and outlets and things like that. So I'm not sure which one you had in there, but yeah, cement treated permeable base. So
that's interesting. And we have folks, have some other sub-consultants that have done a lot of work with recycled pavements and performance of those. And that'd be interesting to visit with them and see what kind of, if they've dealt with that type of situation before.
Okay.
So,
all right. Next one. Why would the agency want to perform cement stabilization of sand subgrades? Why would you ever want to cement stabilize a sand subgrade if it is already fairly drainable and offers good support?
I think with, not commonly. I think the cement treatment will work with sand, but sand's a good base, and unless it's pure sand, where you might have some stability issues, that'd be one time to use it. But it's probably not a common technique. I think the slide that was referring to showed that it would, you can treat with sand, but probably not very often.
Okay, gotcha. Next question is cement stabilization good for sand and clay? This person says typically you use lime for clay and cement for sand.
Okay. Cement, you'll see in these slides, I think coming up, clay is a perfect candidate for improving foundation layer performance with cement.
Okay.
Yeah.
And the last question, actually, I answered when we were talking about recycled concrete, seeing drainage issues with recycled base from the fines that are dissolved and released over time. And the answer is yes. In some cases, we have seen it. It's not extensive, but there have been some instances of that leachate, they call it. It's a calcium carbonate type of material because it's essentially free lime that's in the recycled concrete that then is dissolved and obviously pulls CO2 into it and reacts and creates CaCO3, calcium carbonate, and then that can potentially plug up filter fabrics and drainage systems potentially. So I guess I'll answer that one. All right.
Very good.
Thanks.
All right. Thanks. Good discussion. Good questions from you guys. Thank you. Rounding out the mixture design process, you basically you select a cement dosage, and typically it's, for example, 2%, 4%, and 6%, and you mix up some lab samples, test the density of those mixtures with the different cement, do your Atterberg limits with cement, the cement mixed in, and do your optimum, figure out what your optimum moisture is based on your maximum densities. Do your unconfined compressive strengths of the different cement treated samples, and then you graph them. So, there's a lot more detail in the book on this, but if you think about, your samples of 2% cement, 4% cement, and 6% cement, graph the compressive strength of those samples, and typically you get a pretty linear relationship. And then if you're after, say, 150 psi unconfined compressive strength of that material, that's what you're after, then you can come out, use the graph. And for this example, that tells me I only need 3.5% cement treatment to that subgrade soil to get that unconfined compressive strength. So it's pretty straightforward relationship. Again, a lot more detail in the book. And I talked about the plasticity index. These are this is just an example of that relationship of how cement treatment to cohesive soils on clay soils can really reduce the plasticity index. So we can get a reduction basically of a PI of 42 down to a 12 just by mixing 3% cement with this particular example. So that goes a long ways towards improving the different properties of that subgrade foundation layer. Just a graphical representation. So different 3% here, 3% cement, 5% cement over here, and look at the PI reduction. Some of these from above 40 down to under 25 down to 16. So some extreme reduction of PI, and again, that's what we're after. We're trying to reduce the plastic range of our soils, basically, typically with our clay soils. The construction process is a step-by-step process. I'll just go through that. Typically, we have to identify the problem areas with a proof roll. Moisture conditioning as necessary, depending on where you are and what that, if you've done a lab test and understood what the moisture condition should be prior to your CMS treatment, that's where you're doing that initial conditioning here in the field. Sometimes in initial pulverization to incorporate that moisture to get a uniform moisture of the starting subgrade. Typically, you'll do some preliminary grading because what happens is that you're incorporating cement into that subgrade system and mix it up. It is going to rise. It's going to change your subgrade profile layer. So you want to be able to bring in a little more soil so that after you do this process, you don't want to go back and reincorporate another cement treatment soil if after the process is done, your profile grade's too low. So you got to have enough soil there at the beginning so you can do final trimming after incorporation. So how do we add the cement? There's different ways. There's bulk cement, which this is not a good picture of the dust that can, it's a good depiction of how much dust can be a problem. And this is something I wouldn't recommend doing in a residential area because the bulk cement distribution can be very dusty. This basically you're unloading cement out of a bottom dump truck, basically. Very dusty. I probably wouldn't recommend that. There are slurry cement applications where you inject the slurry right on top of the grade, and then you come back and incorporate that into the grade. There's a slurry train where the actual slurry is injected into a mixing chamber of the reclaimer. And there's also spreader trucks. I think spreader trucks are more common. They're a lot less dusty than the bulk cement application. So they have a better control of, that cement is being distributed there at the back, but they typically can do a pretty good job of applying the dry cement versus the bulk cement type application. All right. There we go. Computer was bogged up there. And then once the cement is applied to the grade, then you bring in the reclaimer equipment. Basically, that's mixing up the soil, injecting water as needed for that to get it to the right moisture content. Here's a photo here showing the water truck feeding water to the reclaimer. Just said that some of the this can be done ahead of time. You can run the water out in front, or you can connect the hose right directly to the reclaimer. You can see different applications of the teeth on these reclaimers. The different soils require different effort to pulverize the soil. And there is actually a gradation that we're after with soils, cement treated subgrades. Basically, I mean, you can go out after the application, take a sample and do gradation. And it's pretty easy for cement stabilized subgrades. We're looking at 100%. So passing 1.5 inch. So it's got to be everything under 1.5 inches, and then 60% passing number 4. So not a lot of testing required on gradation, but you can see the different gradation types. Play a quick video here. This is the reclaimer. So the cement's been added to the mix. This reclaiming device is mixing the subgrade soil and moisture and cement all in one pass. So there you could go and grab a sample, take your gradation. You could also do a distribution or application test. So we need to do at least one test on ensuring how much cement is being applied to the surface. So before that reclaimer goes by, you stick down a 3x3 sheet of carpet or a turf or something. Weigh it, have the cement applicator go by, weigh it again. You can get a quick value of how much cement is being added to the surface. After the reclaiming operation, you come back with a sheep's foot compaction. We're looking for 95% maximum density on that. I got a video there. All seen a sheep's foot roller, I'm sure, but it's just the final step. After that, reclamation is done. The key here is that timing. So cement stabilized subgrades are on a clock, and they will hydrate pretty quickly. So within 2 to 4 hours, we got to get the compaction done because it's already starting to hydrate and perform and go through the hydration steps. So we need to make sure the equipment is there and ready to go. Final steps, grading and trimming. Again, we'd rather trim off excess than having to come back and add cement treated layer on top. And some applications you can do a fog spray or bituminous emulsion type curing to make sure that the hydration process continues. Just like we put cure on a concrete pavement, we want to keep all that hydration water in the material. Weather restrictions, similar to concrete paving, CSS, go on and apply that on frozen ground or on water, should be 40 degrees or higher. There's a 1-hour webinar. If you go to the PCA, Portland Cement Industry, or cement.org, go to this link and those will be in the handouts. You can learn a lot more about CSS. I tried to cover it in 10, 15 slides or less. How do we test these improved subgrade? We're pretty familiar, I think, with the M&D test, compaction to 95% maximum proctor density or standard proctor density. 4% above is typically, that's a local standard, an Iowa standard again. The CBR test is not as common. It's costly. That's lower photo is a CBR test, but M&D tests are good. They provide a very accurate result of compaction. I like to see the dynamic cone penetrometer being used as well as a spot test to identify the strength of the bearing of our soils. And what you're seeing here is a couple profiles from the dynamic cone penetrometer. It plots the CBR over depth. So CBR percent. This is an example of a roadway in Iowa where I had I think a 7 or 8 inch concrete pavement with a 12-inch rock layer, and this was a place where we had some poor performing subgrades, and so they installed a woven geosynthetic layer and on top of the subgrade, and then followed with a crushed limestone, and you can see how that CBR improved in that above that geosynthetic layer. So very good CBR values, and that crushed limestone is staying in place. This is a test done years later. We still have really good CBR values naturally because that rock is bound. It's not going to infiltrate into the soil. And you still have very low CBRs underneath that geosynthetic. So it's doing its job. That system is doing its job there.
Jared, we've got one comment, and
Sure.
it's going back, but you don't need to bring the slides back. But it talks about using cement stabilized sand subgrades again. Well, just a comment on that. You still would get benefits as far as cement stabilizing a sand subgrade, including modulus and strength improvements of that subbase or subgrade, sorry, potentially improving the uniformity if you stabilize it, if there is some uniformity as you go along, some non-uniformity, I should say, and improved construction platform, a better, platform on which to put the next layer. So, and that's in reference to also, we have a couple of long life pavement sections that have been built in recent years in asphalt and concrete. And one of them in particular, I was a little more familiar with, was the 50-year concrete design. Was in an area that did have sandy subgrades, yet they still went ahead and did cement stabilization of that sand to achieve that long life that they were looking for. So,
right,
that's just a comment.
I agree. Yeah, that's good.
Okay, next one is a question: would placement of a geotextile separator and aggregate base be considered satisfactory protection from drying for the purpose of curing of a cement modified or cement stabilized soil? If you said, you still need to cure it, what if we quickly place the geotextile separator and put an ag base down on top of that? And if so, is there a minimum time frame between that final mixing compaction and then when that subsequent layer can be placed?
I don't see a problem with doing that right away. Once you run the reclaimer through and do the final compaction, it can be trimmed and graded, and it can be built on right away. It'll improve those the parameters, or the properties have changed the minutes it's mixed in. Maybe I'd give it an hour, I'd say, but you don't have to wait all day or several hours later to apply the next layer. So, and I think as far as curing, I don't see a problem at all with putting that geotextile and subbase layer down. Maybe wait an hour afterwards and then incorporate the next layer.
Okay, good. Thank you.
It's good. It's a good system. Yeah. The compaction tests are great, but they're spot tests. DCP is a spot test. We really should be doing proof rolls along the corridor. This will identify along the whole route where the weak spots are. And so this will, this is a widespread test of the subgrade, and how it'll identify the ruts will show you where the soft spots are. So in my mind, in my opinion, you should be doing a proof roll on every subgrade, improved subgrade when you're doing with concrete paving or any types of pavement projects, because you're basically testing the whole corridor and you're identifying those soft spots. Couple research projects. This was done a few years back, 2013, 2014, and worked with Dr. White at Iowa State University. And this was really the first quantitative test on subgrade performance, and testing in situ parameters like permeability and the drainage coefficient and the K value of the subgrade soil. And what this study did was test those parameters. Those parameters we often would use for designing a concrete pavement. Your K value, your modulus, your soil modulus, drainage coefficient. Those types of things were tested in the field and compared with concrete performance. So we used the PCI method to evaluate performance, and we developed a relationship between subgrade performance and pavement performance. We all knew that improved foundation layers, whether it be stabilization or rock subbase layers, we all knew those would lead to better performance, but we didn't have the data. So this is the first test where we actually had the data, and there were only 16 sites. And granted, it wasn't a very large study set, but different support conditions. They weren't all good pavements. We looked at some really bad pavements, some good pavements, and what we found really is that everything was variable. We assign these design parameters when we're designing a concrete pavement, where we say we're going to get a great drainage coefficient when we're putting a rock subbase in. That's probably accurate on day one, but 5, 10, 20 years later, things change. And what this study showed is the foundation layer properties changed over time, which we could expect. And we were seeing poor drainage years later on those systems where we had rock on subgrade and we had fines mixing with the aggregate. We lost the drainage property or characteristic of that drainage layer. We're seeing loss of support with voids developing under pavements just based on normal movement of subgrade. More uniform subgrade and higher coefficient of drainage performed better. So we're in those areas where we had good uniformity. We had several comparable K-value tests and modulus tests as we went down the road. Those were good pavements. Higher drainage subbase layers had good pavements. The biggest parameter the biggest takeaway from this whole study was how sensitive the drainage coefficient was. So anything that changes that drainage coefficient had the largest effect on the PCI and the performance of that pavement. And we attributed that to basically over time that soil movement and the mixing of fines with the aggregate and how we get a different property of the subbase years down the road if we don't have a separation layer. And I believe the DOT Michigan does use a separation layer. So I think that's a great system where you put down a woven or non-woven separation layer, put our rock on top of that. And typically, I think you could even reduce some of the subbase layer thicknesses. You can develop similar cost systems, whether it's Iowa DOT puts at least 12 inches of rock under their pavements. So you could maybe compare that to a system with 5 to 8 inches of rock with a good separation layer, cost equivalent. You may have better performance. I think you will have better performance when you have a separation layer there to make sure the fines from the soils are not mixing with the aggregates and causing problems with the drainage. So this study I mentioned earlier, this just came out in January. This is on the website, improving the foundation layers for concrete pavement. Dr. White and his staff and grad students and helpers there at Iowa State University did another study. And I think the first study I just talked about was just step one. This is the step two of the study. I think is a lot better information. This was a pooled fund study with 5 states, California, Iowa, Michigan, Pennsylvania, Wisconsin. Basically similar things are going out in the field to test foundation layer parameters and see what we have in the field, and then understand how we need to improve those parameters for better long-term performance. There's a lot of writing on these slides. I'm not gonna go through them all in depth. I'm not gonna read them to you, but if you think about what we do today, we go out and we design a roadway and we take spot checks. We take our nuclear gauge and do a compaction test here every so many feet. We're not getting a really good verification of the whole system unless we do a proof roll. I think that's a very good technique. The other thing is with the design software now, the AASHTO Pavement ME, this is the MEPDG that several DOTs are using. We assume that we're getting those parameters from day one throughout its life. And I think, as we know, things change over time. So what this study showed was the pavement design software had a low sensitivity to the support provided by the foundation materials. So you couldn't get the program to show poor failure mechanisms or poor models based on varying foundation parameters. So, but as we know, it really does happen in the field. So it's kind of a limitation of pavement ME, I think. Limited geotechnical testing, 1%. So this graph here is some stress versus deformation on I-80 in Iowa. 2 tests taken. 1 test had a K value of 284, which is outstanding for bearing strength. And then just down the road, we had a K value of 39. So this goes to show you the differences in variability that you can get throughout the pavement. Other challenges with current practices: loss of support. Even just a 100th or 800ths of an inch gap or a void under a pavement, up to say a 1/4 inch of loss of support. Those are going to show over time. You're going to have those different values of loss of support over time with additional loadings are going to provide decreased pavement fatigue life. Most of us can understand that. This test proved it based on some studies that it showed. Other things, impact of wetting and drying cycles and geomaterials needs to be evaluated. This is kind of what needs to be understood going forward. Ideally, what we want for long life concrete pavements is uniform support. Great question earlier on what is uniform support. Balance between excessive softness and stiffness, drainage. We don't want permanent deformation of our subgrade soils. We got to do what we can to strengthen those and make them uniform by doing some cement treatment or fly ash treatment or geogrid and rock or woven geosynthetic and rock. Those types of systems are good pavement foundation improvement systems. So the report really proposes, at the end of the day, it proposes a performance-based specification approach. So that specifies the support conditions provided by the foundation layer. And what it's really after is full-scale testing, and you can do with proof rolls or intelligent compaction. And then also we need to report those deficiencies, and we need to have a specification that requires that spatial test, if you will. We need to test every part of the overall subgrade system. The other one thing I'll finish up here, the DOT research, a couple slides from what the DOT is doing and with intelligent compaction. If some of you may be aware of intelligent compaction, it gives you real-time data, real-time reading of subgrade performance and subgrade stability, where you can identify where those values are, even if they're not readily apparent by the rutting that you would see with the smooth drum roller. But then you can go back and rework those areas and test them. So what's going on at Iowa DOT is they're doing some pilot studies with intelligent compaction and requiring the contractor to have a smooth drum roller, and then the DOT would provide the intelligent compaction system to hook up to that roller and be able to test these. So it's not forcing this new technology onto the contractor, but it's kind of side-by-side pilot testing at this point. And then finally, one of the things they're studying is open graded structures and how does the current compaction specification on open drainage subbase system affect drainage and stiffness. And what they found to date, comparing an open graded subbase to a modified subbase or a medium drainable subbase is, we do see a difference in the amount of time that it takes to drain. It does affect drainage. when you change from a open graded system to a modified system. But what this is showing that they stay fairly uniform. I mean, these are 1 pass up to 24 passes based on different sites. And whether we're comparing crushed limestone, recycled concrete, and then mixtures of recycled and crushed limestone. So we're not seeing a lot of big differences with based on drainage, impact of drainage. So that so far hasn't been a big factor. I think they'll continue to test these types of relationships with the open graded systems and the modified subbase, which is a kind of moderate level drainage system, and see how drainage is affected and long-term consolidation is affected as well. So I went over, but some good questions there. Steve, if there's any other questions, I'd be glad to entertain those.
Yep, we've got a couple. First, one is going back to kind of the history as far as many agencies were stabilizing clay soils with lime or fly ash historically. You'd get into a clay site and you dry up the soil with some lime, disc that in and dry out the soil essentially and make it workable. In recent years, a lot of agencies have been transitioning to cement stabilization, cement modification, with those clay soils. Do you have any perspective on why we've seen that shift? Historically, lime's been great. Why are we seeing a push or a desire maybe for cement stabilization?
I can think of two benefits versus lime. As cement is permanent. I think lime is a good product, but we know that cement will provide long-term stability. It also works faster. So in our real world where we can't wait 2 days to let the soil dry out, we got to treat it and change the properties and move on. So I think the lime system has a mellowing period. We have to wait longer before you can get on it and start building the subgrade, building this foundation support system versus cement treated soils, wait that 1 hour, 1 to 2 hours to get that process completed and continue building the roadway. So I think time is a big component, and then the permanency of stability of that system.
Yep. Okay, good. The next two, feel free to keep typing questions in if you have some, but the next two are on proof rolling. Number one is, do you specify the equipment or loads to be used for proof rolling? Maybe you're more familiar with Iowa's spec for that, but is it say what the load needs to be?
Yeah, that's basically the Iowa spec specifies a loaded tandem axle truck, and it needs to be better defined. We've debated about this at the office, but they say a fully loaded tandem axle truck, using that equipment for proof rolling. I think it should go as far as specifying the weight as well, but most of us can go from there.
Yeah.
But yeah.
Gotcha. Typically, probably loaded with soil, sand, gravel, aggregate, whatever it is. Okay. So that answers that one. And then the second one on proof rolling, proof roll test after stabilization, your slide indicates up to 2-inch rutting under the proof roll truck is okay. Do we want to permit that much of rutting and still accept that subgrade?
No, that may be a mistake in that slide. I'll have to look at that proof roll. I wouldn't be comfortable with the 2-inch rut.
Okay. All right.
So I apologize for that. I'll have to look into that. But
gotcha. Especially if it's after stabilization. I mean,
right. You shouldn't get anything really.
Yeah. Maybe on an untreated subgrade, maybe that was something that you would allow, perhaps. But next question is on this intelligent compaction, which you finished up with near the end here. How many states do you know of that have initiated intelligent compaction on new concrete paving projects?
I would say very few. Dr. White when he was at Iowa State University. It was just kind of his uh, his baby, if you will. He's now has his own consultant company, and he's doing these around the nation. But I think Iowa's probably at the forefront of this intelligent compaction, and even Iowa's not specifying yet. They have a long-term plan of 5 years to implement this. I think it'll be long, maybe could be longer than 5 years, but we're just starting at doing some pilot studies and side-by-side testing at this point. So I would say very few, I don't know for sure, but I would guess very few states have specified it, or maybe some have used it. I know Dr. White has brought his equipment to different states on a per project basis to meet a special provision of a certain project, but not a standard specification for states.
Okay. I will add that I sat in on that webinar that was it Melissa, I think?
Yeah.
Serial from Iowa DOT. She was the one, Earthworks engineer, I think is her title at Iowa DOT. She gave that presentation, did a great job, and you only had a couple of slides from it, but it's an excellent research and really cool to show that, the roller and the mapping.
Yeah.
And everything else. And how it all tied together. So a research project with some real practical usage. So it hasn't come yet to round out answering that last question. It hasn't really come full scale to everyone yet, but I think that is the future to compact intelligently, to know where we need to compact or know, maybe have some feedback to what type of soils we're compacting up against, and maybe areas that need some more rework. So,
yep, the technology's there. It's been here a long time. It's just getting industry to buy into it, and the agencies to understand that it can be done. And I think that's the future. And I put the slide up that shows you can go to the CP Tech Center website and go to the events page, past webinars. You can find the Melissa's. I think it's about a 50-minute presentation. It's good stuff.
Yeah. All right. One last question before we end this morning. What are some states that use cement stabilized soil methods as standard practice? Does Iowa, or is it only used in specific projects, demonstration? Is it a regular practice that you know of around the country?
It is a regular practice. I don't know. I can't give you a list of states off the bat. I know Iowa's done it. I know Texas has done it. I'm thinking of the TAC members that helped produce that guide. If you go to that, the CP Tech Center website, or search the guide, the cement stabilized subgrade soils guide, it'll talk about that, and it's becoming more and more widespread. I think a number of states are using it or allowing it in their specifications. It's going to take time to get more people to try it out and adapt to it. But locally in Iowa, we've seen as we're in the central Iowa, we're some of our ready mix producers are seeing the effects of the fly ash shortage. So even on subgrade support systems, we're seeing more cement being applied for subgrade improvements than we would typically see fly ash all the time. Now we're seeing more applications of cement treated. So I think it's going to become more and popular.
Yep. I would echo that and agree. All right. Just to wrap up here, just want to say thanks to Jared for his participation and presenting that this morning. We appreciate that, Jared. Just to wrap up here. We want to say thanks to our sponsors as well. Superior Materials, the Levy Company, and St. Mary's Cement are our three primary sponsors of our entire webinar series. So we want to thank those companies. We've been recording this and have the handouts as well. Those will be up on our website. Follow that link. Just go to our website and click the links to find our annual conference information. So that should be up by tomorrow as well. Keep an eye on social media. We've been highlighting all of our awards projects. Today was in decorative interior floor of a building that was done over here in West Michigan, where I am. And we've got 2 more webinars still scheduled. We've got Thursday this week, where we're going to talk about insulated concrete forms for commercial construction. And then we've got Tuesday of next week, where we're going to discuss kind of wrapping it all up with a lot of different technologies all in one type of project. So 2 more opportunities to get some more continuing education hours. But again, thanks to Jared and the CP Tech Center and Snyder and Associates for allowing him to present this morning. And thanks to all those of you who tuned in. We appreciate it and look forward to seeing you all at some point in the future. So take care, everyone. Hope to see you soon. Thanks.